Hi, my name is Andrew McLaren, and I'm going to help you solve projectile motion problems like the one that we have in front of us, the way a human would, aka not using quadratic equations, which can be tricky and oftentimes incorrect because we mess up the steps. So if you want to be able to at least double check your quadratic equation, this is a tip that I've used with a lot of my students that I tutor, and I highly recommend it. So when you have projectile motion where something is going up and then down, there's this symmetry that you can look at where as much time it takes to go up is how much time it would take to go down from a given height in that projectile motion. So this is a pretty useful thing in a problem like this because we can look at what I've got labeled in blue right here, this first section, and that's like how much time it takes to go up to its maximum height. And then in green, it's like going back down to that original height. And then in orange, I've got it going down all the way to the bottom. Sometimes it's useful to break down the motion into all those segments. For this particular problem, we can avoid the quadratic by solving for the time that it takes to do this blue section, and then also solving for the time that it takes to do this purple section and adding those up. Now, this is going to be pretty easy if we try and focus on finding that v final. And this will allow us to just do math without quadratics, because if we look at the original problem, you do have an original velocity, you do have an acceleration that is implied if we're talking about Earth, and we have a distance here. So we should be able to, in theory, solve for this. It's just the math is not very pretty for us humans. So if we want to do this first section, we're going up to some sort of height, but at that height, the velocity is zero. Like it's v final for this blue section, or the velocity right at the top is zero because the moment before is positive and the moment after is negative. Right in between, we've got zero. So if we wanted to take our positive velocity of 6.2 meters per second, and we want to figure out how long it takes for that to get to some sort of final velocity of zero, we can use this formula right here. It wasn't really that useful in the original problem because we don't really know what that final velocity is at first. We can actually use some numbers at the end to confirm that. But for this first section, we can use a acceleration of negative 9.8 meters per second, which is equal to some sort of change in t over the v final minus v initial. So we've got 0 meters per second minus our 6.2 meters per second. And we can see that we have everything that we need besides that change in t. So a little calculator work should show us that luckily it's just this negative 6.2 on top when we do that math. And we can look at that as just like kind of rearranging this. So we take that negative 6.2 and we divide it by the negative 9.8 when we rearrange that. Because they're both negatives, I'm just going to do that first one divided by that second one. So that's how much time it takes for it to just get up to its maximal position. So 0.632, just going to have an extra sig fig on there just in case. So that actually means that this first number that we want to look at for this first time is actually now known, and it's 0.632. Meaning also this time for it to go back down, that amount of distance would also be 6.32. I don't think that's particularly useful in this problem, but it lets us know that at least a second, like 1.3 seconds is going by. Probably a bit more because we still have to go that orange distance down ultimately. So we get up to that final point up there, and then what we want to do, the easiest way of doing this is now trying to solve for a time for it going down. But we're going to need a distance that's appropriate for that. So we want to know what the change is in distance for this purple motion. If we do know that, then we can plug in some relevant numbers. So if we wanted to look at the reason that we're doing that is because if we have this change in x formula, e naught t plus at squared over 2. Actually, I think I forgot that part in this formula in the original problem. But if we look here, the v naught for the purple motion, that is 0, meaning we don't even have to take into account that part of the formula. So we've avoided the quadratic now, if we have this change in distance. So we need to know how far we're falling. We know the acceleration. So if we have this information, which is something we can find, we know this acceleration, we should be able to solve for this, this t for it to go down. The problem is that we need to now figure out how high up we are when we're at that maximum point in the projectile motion. We can easily get that though with the blue motion here. We know its final velocity, we know its time, we know its acceleration, so it is something where we can just kind of plug that in and figure out using its change in x, the v naught, the time that we're working with, and the acceleration. All of that is known and something that we can work with. So we know this velocity, that's something that's known, you know, this acceleration, and we have the time that it takes to get up to that highest point, which was that 0.632. Drawing a diagram on this problem does help. I know this is a fair amount more steps than using the quadratic, but it lets you actually know your answer. So if we look at our initial velocity, it was a positive 6.3 up, or 6.2 meters per second, positive number, times that by the time that it was going up. Those are both known, because the v initial for the blue motion as well as the overall thing is at 6.2. And then we have our acceleration at negative 9.8 meters per second. And we've got our time, 0.632 seconds, which will be squared all over 2. I'm realizing that we're running out of room, so I'm just gonna move some of this stuff over. We'll get to it later. But for now, it's just a little bit of calculator work. We got that 6.2 meters per second times the 0.632. And that's going to contribute this. And then we're going to have the 0.632 over here, which is being squared. So we'll go ahead and square that. Times that by 9.8, or negative 9.8. And divide that by 2. And this is going to be a negative 1.957. Okay, so we add those two numbers up with a few extra sig figs just to, you know, be careful. And we're getting 1.960. Those worked out to being very close. These 1.9s just happen to be with this problem pretty close. If we'd given it a different velocity, it might not have split so evenly. So we've got that number for the distance that it goes to get up to that maximum point. We got 1.9608 meters up, meaning that when we're falling, we've got that in addition to these 46 meters. So going up here, we have that 1.96 number. So our change in distance now is that 46 plus this other one. So we've got 47.9. It is limited to the 2 sig figs and ending in that 1's value here. So we are really looking at something that's more like 48. I'm going to keep the raw number though, because we weren't asked to report that number. We're not going to round in these middle steps unless asked for a reported number for that distance. So now we have that 47.96 meters, and it is falling that distance. So that's a negative change in x. So we've got that is this number right here. And then we've got our acceleration, or the negative 9.8 meters per second squared, times some unknown amount of time, all over 2. So we do a little bit of math here. I usually try and isolate for the t squared, just to give myself something I can check. So we've got that 47.96. We're going to times that by 2, it looks like, and then divide that by 9.8. So I'm getting 9.78 something for the t squared. Let me just isolate for t squared, and then you just get the square root of that. Okay, so that's going to be 3.12 seconds. For it to fall downwards now. So for it to go down, we've got this now. This new time is 3.2 or 3.12. So we now know the time that it took to go up to that top point and the time that it takes to fall down. So the t total is just the addition of those two from what we've got here. So the 0.632 from the part of the motion that I've got written in blue, plus 3.128 seconds from it falling down. We add those up. And we get about 3.76. Which, if we're limiting it to the 2 sig figs that were provided, that should be about 3.8 seconds for it to do this this motion that we've got marked in black right now for the total. And that is how I would recommend to do this as a human. You can now actually plug that in and see if that is correct with something. You could do the quadratic problem and do that. Or what you could do is say, like, okay, if I have a change in x and that v naught and that time, does that actually solve this equation? So you can go ahead and plug these numbers in, knowing that it fell 46 meters. It had an initial velocity of 6.2 meters per second, and we're saying this is 3.8 seconds for how long this would take. This acceleration, do not forget the negative. That would be an easy mistake to make, but one that's going to be like a critical fail for you D&D nerds, right? There's some of you in a physics class, I know it. So we've got that 6.2 times 3.8. So that's going to be 3.6. And then we've got that 3.8 right here being squared for that time times 9.8, but it's a negative. And then we're going to divide that by 2. So 70 point, what is that? 75. We add those up. It does look like, to me, just kind of spitballing. That looks pretty close. So negative 70, yeah. And then we add that 23 point, was it 5.8? It's 5.8. 5.6. Small mistake in the calculator work here. Let's just double check that. So there's actually nothing wrong with our calculations. We were just using the estimated number based off of our level of precision that we can really say, given that we're working with 46 meters and 6.2 meters. So we limited that to 2 sig figs, which is the correct answer. But if you want to just do like the raw numbers relationship or the calculation, you really should use the number that you get when you just don't round. If you just get that 3.76, so on, so on, so on. That number, if you plug that in here, the 3.76, it cancels out a bit more precisely. We were very close with our other numbers, so I thought it was just a small error in rounding, but it actually was the fact that to get the quadratic equation to be correct, we're just doing the math and ignoring the level of precision. And as you can see here, when you multiply that, for example, the 6.2 times the 3.76, we do get a slightly different number. And same here. And when we add those two together, and you can double check this if you'd like, you get pretty much 46. It's very, very close, within a reasonable degree being off, given that this is only accurate to 2 sig figs that we're talking about here. And those numbers are coming out to be like almost like 4 or 5 sig figs needed to have them deviate or be slightly different. So I feel very confident in our final answer. You can double check it with the quadratic as well. It's also interesting to note that it took definitely more than the 1.2 seconds for this just to go up and down. And then we've got this 3 seconds for it to go the whole way. If you wanted to, you could also do another calculation. I'm going to leave this to you as a way to double check this, but you could find out what is the time for this thing to go and fall down all the way to that orange segment, and that should be something that you can do, kind of like what we did with the purple here, knowing now though that there's a negative 6.2 meters per second. It's going downward at that I don't know, v2 we could call that, when we're at the same height, we're going the same speed here. So this could be maybe like a v2 that we're talking about. And you can figure out how long it would take for that to go down its distance. It's kind of nice knowing that the v final, we already have that. So you could use that final velocity and that negative 6.2 to see how much time that would take, and double check it. Way better than just trusting your calculator. I know that took a little bit of time to do, but if you're doing a quadratic, you're either plugging it into just like something that does it for you very quickly, or you're gonna spend some time doing that calculation as well. And I'd rather know if my answer is correct than just trust the machines, right? Which, interestingly enough, I actually asked ChatGPT to solve this problem and do it a similar way, or how a human would do it. So I said, can you solve this problem like a human would? And it ended up doing the quadratic, which is doable. That's fine. It's tricky for people to do that reliably. Also, the quadratic formula, people try and memorize and they get it incorrect. Then if you asked it to break it down without the quadratic and it actually solved it in the way that I had previously thought of on my own, it is not giving this to the correct number of sig figs. So I'm just going to ask it about that for this problem and just see what it says, because I've got a feeling that, yeah, okay, it did it correctly in this one. It wasn't too complicated. Oftentimes it messes up sig figs, but it did all right that time. Maybe it's getting better. I was editing the video and I noticed that ChatGPT actually did round a number in the calculation. A little bit earlier, it found the 48 meters. It rounded it to 48, which in this case worked out not being a big problem, but sometimes that would. So it's not even following its own advice here, not to round intermediate numbers. It knows better. But unfortunately, it didn't follow that on the first pass through. So just be careful with those rounding of the in-between numbers, as I was saying, and they're also confirming, don't round too early.